Alright, time for another draftphysics.com, debatephysics.com also. Video presentation. Okay, same stuff really. So, Steve Mould, as context, basically is arguing that levers don't conserve momentum. That something makes the momentum disappear essentially because there's no real explanation for where it would go. So anyway, the simple case is you can have let's just say these were two masses. You could drop a two mass one distance, and then on the other side you would have the expectation that this leaves with pretty much the momentum that went in here. Now obviously, I shouldn't even say obviously anymore, just because nothing apparently is obvious to scientists. The lever itself has to move, and so it's going to consume some percentage of this momentum because it's going to make the lever move. And the lever moving will be absorbing some momentum in the process of moving. Something. Anyway, so you got a pretty good expectation. You're going to get 90%, 99, who knows? Pretty good percentage of your energy back. And then if you put a half mass, okay, two distances, the law of the lever basically says, well, it said it for thousands of years until a month ago, that you would have the expectation that it would leave with twice the velocity. Okay, so it's no problem. Now the kinetic energy theory says that can't happen because effectively I could have, as they would say, 2 joules going in here, and I could end up with 4 joules coming out here. All right, so I'd end up doubling the amount of energy, even though the momentum is exactly the same. So that's the problem with that. And so they claim, they don't show it with any evidence, that this can only leave with 1.4 the velocity. So a huge degrade in its function. 30% of the momentum disappears, so it can leave at 1.4. Now the other consequence of that is all these kind of lever experiments should be perfectly reversible. That is, whatever you can make happen by stuff here popping out here, you should be able to put the stuff in here and have it pop out the other side. That is, light objects going fast should be able to make heavy objects going slow just as easily as heavy objects going slow make objects go fast. So their argument basically is I could take a portion of the momentum, say if it was 60, and I could make 100 momentums pop out the other side if I reverse the experiment. Obviously, free momentum. So, and apparently modern physicists don't see any problem in destroying momentum and creating free momentum. So even though momentum, as Professor Loom would say, nature can't finagle momentum, apparently it can. Yeah, you just have to talk to a different physicist, and it's just fine. So that's the paradox part. So in this video, I will attempt to provide an explanation for how the universe works, where you can understand why momentum nature can't finagle it is because it is as it's reliable as the number of photons hitting something. All the forces that we are interacting with in the physics is so strict and so reliable, and momentum is playing by the same rules. It is quantizable. People should find that appealing, actually, that somebody's arguing that momentum, force, energy is in discrete, definable chunks. It's just that their definition is so small. Okay, their discreteness is so discrete, tiny, that it's a little bit hard to perceive it that way because we can only deal with millions of them at a time versus any one of them at a time. The other part of it is it sort of makes it clear, that you can understand the universe is one universe. That in one part of the big universe and the getting very small, there's a place where everything has to sort of happen, where the real math is done. And I'd argue I'm also giving you that in the sense that it can really be understood as it was understood, say, 150 years ago or so. Um, that's really just about electrons and protons and them being manipulated by force. And that's really the whole story. That's where the real universe is, and everything else emerges out of that function. So I guess we will show you that first, the simulation again, and then we'll just go through the description of how you really have to understand there's, it's just stuff being pushed this way and then stuff being pushed that way, and it decides to go in the direction where it gets pushed more. It's pretty much that simple. Alright, so there's the simulation. Okay. And very, very simple rules. It basically creates the exact Maxwellian function of electrons and protons, charges. Okay, plus, minus, if you want to put it that way. It was the same rules pretty much would obey if you could make magnetic monopoles, in the sense that if you understood electrons and protons to be magnetic monopoles, the behavior would be pretty much identical. And it simply illustrates the creation of more complex arrangements between electrons and protons, in the sense that they will tend to associate with each other, become neutrons, and then become deuterons. Okay, and I don't know what the next version would be called. But anyway, those mechanisms would be able to create the circumstances that you see in a lot of ways, in the sense that you could duplicate also the strong force, in the sense that you could understand that there would be a tendency for the creation of something like an electron and then a proton on either side of it, very close, and that you could eject the electron by hitting it with the appropriate force, and you'd end up with two protons very close to each other, which mathematically by their function would necessitate a very expedient separation, a lot of energy. So anyway, so yeah, it's just really simple rules, push rules. Okay, it's just a push-averse. And so I'll go through some of the simple mechanics, but the idea is there actually is this discrete force, illustrated as the little blue, green things, little red things flying around, and they have an inverse relationship to the electron and proton, and that's all you need. You hit it when it's, well, I'll probably best to draw it, but you can see the arrangement quickly does what logically makes sense. North, south, north, south, north, south, or plus, minus, plus, minus, plus, minus is the arrangement. And you're off to the creation of a nucleus, and the next step would be the atom, and the next step would be the chemistry. And it's all going to be governed by these simple rules, because this is the only place anything really happens in the universe, is your electrons and protons are in an environment, and that environment controls what happens to them, how they behave, because there's a bunch of force created by all of their arrangement. They, like the solar system, they create a bunch of complex gravity. So that's also the point here, is this also illustrates the source of gravity as a real force. It's not some kind of bent, fake, geodesic thingy. It's not some nothing, some bent nothing. It's a real force, and all you're really saying is that objects can absorb energy as it passes through them, and that creates a deficit that other objects get pushed into. It really is it really is understandable as something that simple. Again, it was proposed 400 years ago, or 300 whatever, 62 years ago, by a guy named Fadio, who was a friend of Newton's, a very good friend for a decade or so. And he first proposed a particulate gravity. And yeah, there was problems that didn't, that they couldn't understand, just because they didn't really understand heat was just another form of momentum and all of that kind of stuff. So, they saw some problems that were insurmountable at the time, and but with more careful analysis, it can be understood that the problems really aren't problems. So anyway, back to drawing, I think. Alright, so let's say you started with a universe that just was perfectly randomized, in the sense there was just a bit of little tiny things moving the speed of light for whatever reason. Little tiny golf balls. And they had two forms, electron force and proton force, we just call them, based on how they react with electron and protons. Obviously, they could be the origin of the story and then be called something other than Dave's brother, but they're sort of stuck being called something else because we can't find them first. We have to find them after we find something else. So anyway, but that's what the universe is made out of. And for some reason, let's just say, some of this stuff turns into dead stuff. That is, stuff that doesn't move anymore. Mass. Okay, so electrons and protons, to be more specific. And they don't have any innate capacity to move. Okay, they're just dead pieces of stuff. So if you could imagine this random field, and if I did put something in here, and let's just say the rule is that the only thing that reflects are the red bits, you could understand that if I knew what was flying in the universe, I could be looking at it from this point of view, okay, and I would see that object, even though, I don't have a way of seeing it besides seeing the fact that it's going to reflect stuff that shouldn't be reflected, stuff that should have to travel the other side of the universe to bounce back, or some other kind of rule. But I'm going to see more red stuff coming back than should be there. And so everything, as soon as I put an object in space, I've changed the space. So the simple rule is that as the blue stuff goes into the red object, it turns into a red bit. So this red object, proton, whatever, is going to be reflecting all the red bits that hit it in the direction it's not moving. So any opposing, any conflicting interaction between this piece of matter and the force bits will create a reflection. And any interaction where they're both going in the same direction, it will be an absorption, and that'll be the nature of momentum. Is the idea that the bit, okay, has a velocity. That is, it's acquired a couple of bits of force, and then another bit of force hits it and gives it more velocity in this direction. So it's just a percentage of the speed of light, 10% we could say for each little bit, something like that, gradually declining, 10% of however short the speed of light you are. So you never can go, the matter can never go faster than the force, even if it collects a whole bunch of imbalance. And the only way it can collect it is through imbalance. That is, it has to be hit less this direction than it's hit in this direction. So if an opposing bit hits it, it hits, if it's going this way, and it's going to reflect, and the one of these little bits will leave. And so that's how it loses its momentum, its velocity, is that opposing force causes it to lose 1 unit of its momentum per interaction with an opposing force. And so it can only go that way or that way, and it can't collect energy in both directions, you can understand. So there's no way to collect a bunch of force in both directions or have canceling. There's no canceled momentum in the elemental universe. You either have in your lifetime had an imbalance in this direction, or you have an imbalance in that direction, or that both were perfectly balanced and you're not moving. So you can understand that the odds of an electron or proton not moving are pretty thin, just because of the density of the universe and the fact that you're going to have a bias in some direction. overall. But you can understand that once these things start crowding each other, okay, you end up with a whole bunch of electrons and protons all spewing force at each other, that they're going to convert into a different force and all that kind of stuff, that the whole environment gets controlled. So the randomness that's in the big universe, that is the open universe, becomes a lot less random, okay? Once you start making smaller and smaller packages all next to each other, they start radiating just one environment. So you could sort of think of a magnet as a good example, is that, you know, it's radiating something different at one end than it's radiating in the other end, and that these environments are real, you know, that, and they control how something sensitive to that difference will behave. So magnetism is all part of this story. It just gets a little complicated because it just has to do with the exposure you have to something. So, you know, if I had an electron and a proton, you could understand that if you're close to the electron, it blocks out the proton, okay, entirely. And as you get closer and closer, there's more chance you can see the proton. So any movement here, it doesn't matter. I can't see the proton, barely. But any movement here, you know, makes the proton visible. So you could understand that it's all about perspective and distances and all of that kind of stuff, depending on how far away from something what you're going to see. So for example, you could have a neutron where you have a proton and an electron very close to each other. And you could understand that from a distance, that would look purple or violet, rather than blue and red. I wouldn't be able to see the blue and red part because from a distance it's all blended together. I'm getting it's, you know, stuff this way and stuff this way, radiating off the two colors, and they're mixing. But the closer and closer I get, the more I'll be able to see that it's polarized. And if I get really close from the right perspective, it's going to look like it's more red than blue. And from some other perspective, it's going to look very blue and not very red. So depending on what point of view I have, I'm going to see something very different. So it all, in my opinion, this makes perfectly good sense. It's a nice, simple illustration of function. And people of scientific mind should find it intriguing and interesting that the universe really can be described with such simple mechanical rules. So we'll go over those one more time and such. Hip cup burping or something. I don't know what the hell that is. Old, tired, irritable. I think I'll throw in a different kind of way of understanding the connectivity between these, you know, how it all kind of relates to each other. So this is going to be a gravitational model, and you're arguing like what's causing gravity, right? So, you know, the idea of this invisible bent space thing is no mechanism. There's no physical explanation. It's not really physics. It's more some kind of mysticism, the magical pullness force thingy stuff. When you can understand that, yes, there's a bunch of force from the universe affecting both objects from the outside, okay, and that is relatively consistent. Now, obviously, you could have the Earth and the Moon, and then you could have the Sun over here, and you understand that, oh yeah, well, there's the Sun-Earth relationship, and then the Earth-Moon relationship, and those are all inside of each other. And so that's, as pointed out, where, you know, the environments get isolated and changed. But you can understand it's basically the same mechanism. Whether I make this the sun and this the earth, or I make this the earth and the moon, I can expand it in any direction, and you can get the idea that it's just about the fact that, so you have an external circumstance that's somewhat similar in expectation, except they're all moving. You know, if there's movement, these two objects, the Earth and the Moon, are both moving towards the sun, but they have a velocity that keeps them from falling into the sun. But anyway, so the point is that you can, you know, it's not, it doesn't take much of a reach of understanding to recognize that all I need to do is have some way that this going through something is different than not going through it, right? So if a force bit, one of the little tiny bits of force, has to be delayed in getting through matter, then you can understand why there might be an effect, in the sense that obviously this universe doesn't get here. So the pressure that's here, okay, going this way, here, isn't the same as the pressure here. The stuff going this way doesn't really make it to this other side in the same condition. And that's why the moon perceives there to be an imbalance and is moved towards the earth, and vice versa, based on how much you change the force by having your matter in the way. Now, the idea of how Brownian motion comes into this is you can understand that as something is progressing, say an electron is being pushed along, it's constantly plowing into an opposing force. So it's constantly going forward, but going back and then going forward. You know, its velocity is not consistent, in the sense that it's constantly vibrating. So if it wasn't moving at all, in terms of it didn't have a way to go, but it wasn't in a universe where everything already had a direction. Like, we're all moving together. Me, the atmosphere, the floor, we're all got the same trajectory, a common one, and then we can separate from each other from that common circumstance. So, the simple idea is that Brownian motion is this idea that we can't see anything, with microscopes, because this happens. So as you get to the really small stuff, everything just starts doing this, and there's no point in looking at it because it's doing this and you can't see it. And you could understand that if something was actually going this way and then going that way, that would be a lot of wasted energy, right? Because you're doing a lot of this, but you're not getting anywhere. You're essentially stuck doing this. So you can understand that, yes, even though this has a direction, there's still a lot of this in it, okay? There's a lot of, it's doing it the hard way. And so it's really degraded in terms of, it's far short of the speed of light because of all of this. And so essentially you could argue Brownian motion consumes energy, in the sense it occupies it, stores it as this, and that's why it doesn't get to the other side. And that's the deficit that everything falls into, called gravity. The deficit is just made out of the fact that there's waste in motion, and the mechanism causing motion has some waste in it, in the sense that it's constantly redefining conditions. Every gazillionth of a second, an electron is changing its condition, its vector, its momentum. And all those changes might have a net outcome. Yeah, it's going a quarter of the speed of the light in that direction, but it's not going a quarter of the speed of light in that direction. It's doing this, and to get there, it's not going a quarter of the speed of light because it's not going faster than that. It is probably going faster, but it can only get there that way because of all of this motion. So another connection is all I'm pointing out. Another way where this mechanical theory explains something we do observe, and it ties it all up into, wraps it into a nice explanation for other things. The different modeling different things with this same mechanism works. It provides a reasonable explanation for what you observe, and that's another pretty strong argument in defense of, yes, these mechanical system explanations can work, and it's just really unfortunate that people are such traditionalists, and they're so stuck to believing. You really haven't seen anything. You haven't seen any evidence of any bent geodesic space thing. all you've seen is the evidence of the inverse square law that Newton discovered. You haven't seen anything else. I mean, all the relativity talk, all the other Einstein crap, it's all beyond our capacity to see any of it. So it's not really relevant, is it? You're not really obligated to believe because there really isn't anything showing that to mean anything. Now, the atomic clock thing is the atomic clock thing. Okay, so if you believe atomic clocks are incapable of being screwed up, that is, you can't do anything to them environmentally to make them tell the wrong time, like every other clock, fine, you can believe they're, magical clocks that can't be broken. But the simple explanation is that, yes, velocity might degrade, okay, the speed at which radioactive isotopes decay. Just might be a fact. And that simple explanation pretty much does away with any kind of evidence related to any kind of notion of time distortion. Like somehow actual time is being bent or distorted, when you can perfectly reasonably believe the only thing being distorted is the capacity of the clock to tell time. You're just breaking clocks. You're not breaking time. Alright, let's see where else to go. Alright, just one more. Relating to charge and electricity and magnetism, and just showing the way you can understand the connection between these things. I should be able to erase that. Yeah, I am. Alright, try to get in the center of the screen here somewhere. So let's just say that we had an atom. We have a net positive nucleus. It's not all positive, it's just net positive. Okay, it's full of neutrons, electrons, and protons, very close to each other. So it has twice the number of protons than it has electrons in it, and therefore it's net positive. So anyway, and then we have the weakly bound electrons, you can imagine. So the simple argument is when electricity is getting pushed into an atom, what it's doing, okay, is it's basically going to hit an electron, let's say this one, and push it in, okay? And the reason why it's in this position is because there's a repelling force from these other electrons. So even though it's attracted to the net positive nucleus, it really can't go towards it because of this repelling pressure from the electrons, the other electrons, and inside the nucleus itself there still are these electrons. So even though there might be a proton right here, okay, in the nucleus, and it's attracting the electron, these other electrons are repelling, sending force, a repelling force, a reflecting force, or change in direction force, a decelerating force, okay, however you want to describe it. So anyway, you push into the field, and what's going to happen is these electrons are going to pop out, right? Probably shouldn't do that in red, but I did. So you can sort of understand, you put pressure in, you end up with pressure pushing out in these other directions, and part of that pressure will be probably directional, so some of it will go this way, you could understand, and that's going to affect this electron eventually, would be the argument. But the point is you're going to change the shape of the atom. So you can understand that if something was looking at these atoms from over here, what they're going to see, okay, is that the atom's now changed. These electrons have moved towards me, okay? And so that's the phenomenon of the induction, is that the external field is now not going to be a mixed field. It's going to be more of this and less of this, okay, hitting a certain location. So you can understand why distorting the atoms by pumping electrons is going to end up, polarizing them essentially, and causing their features to be more visible in terms of their polarization. Now you can understand that this way it's going to look like a positive nucleus, but all I have to do is move this electron, and all of a sudden it's not going to be looking at nearly as positive. So you're just changing the red and the blue mixture into purples, and then red and blue. Purple, red and blue. Well, something like that. Yeah, purple, and then red, and then an opposite purple. Anyway, so it's another explanation where you just understand that what's happening when electricity is going through atoms is that the atoms are being distorted sequentially. Okay, this one gets distorted, then this one, and they're sharing the pressure because all the electrons are connected within this substance, especially metals. All the electrons can feel each other's existence. I move one electron, all the other electrons are going to get jiggled by that motion. So you can understand that you're really changing everything as you move electricity through, and you're doing it in a sequential way. This one changes, this one changes, this one changes, this one changes, you know. And so as you increase the positive here, let's say, well, let's use the correct vernacular, the extra electrons. You pump in extra electrons. Those electrons have to push on all the other electrons, and you're just moving the pushing force through the material, right? And so the faster the electron moves, the faster that jerk. The slower it moves, the slower the jerk. The slower it is, another good example is that you can understand when something moves fast, there's very little stuff that's going to be going in sideways directions. And if it's going slow, it leaks a lot more of its energy in the form of friction, so to speak. Its connectivity to everything else, it has time to push all the other electrons. But if it goes very fast, the electron here doesn't even know this one switched because it did it so quickly. There's so little field change. But if it's moving slowly, there's lots of field change, and it feels it and it moves a lot more. So the faster the electrons are moving, the higher the voltage. Okay, the fewer electrons you need to get the electricity through the wire gets less hot. The lower the voltage, the more electrons you need to actually move, even though you're moving them slower. So you have to use a lot more electrons, and so you end up using more of the wire, more of the atoms. And then the more atoms you use, the more atoms you have polarized, therefore the more magnetic the wire is going to get, because you have a lot of distorted atoms in the material. So low voltages make magnetism, because low voltages change a lot of atoms and polarize a lot of atoms. High voltages change only a few, therefore no magnetism. So it all fits again. Just illustrating that point that the explanation does work, and works well. Alright, so let's bring this back around to the lever. Okay. And the simple reason why you have to understand that momentum has to be conserved, and that's really just saying force has to be conserved. So because of gravity, we have a body that's accelerating. So it's gotten more energy this way, going down, than energy coming up from the Earth. And so therefore it is accelerated, attained velocity, because it's got electrons that have more little bits of energy going this way than they have going the opposite way. So that's why they have collected force. All right, and they're going to hit the lever, and now they're going to meet an opposing electrons that are going to be creating a field resisting, and now they're going to have to convert an electron shooting its rays this way is meeting an electron shooting rays this way, and they're going to have to reflect, okay, their energy at each other and change their disposition. They're going to balance to each other, in the sense that if this one keeps moving, this one has to start moving away. And if this is so many of these electrons, if there's a lot more of them, it's much heavier, denser material. It has a lot of these little bits of force to give away, opposing this, and then it can cause it to go away instead. And it's just a battle between who's got the denser amount of force, and that's why the object with more momentum wins the decision. So any fight between the two things, the one with more momentum, more total bits, is going to win, because the bits are really what's going to determine who's got more energy force. And it's just as simple as saying momentum is force. And you're just saying who has more force, whoever has more force wins. And the win is going to be you've either lost some velocity and you've given away a big hunk of it in terms of you've excreted it at the enemy, so to speak, and caused the enemy to retreat. So you've lost that energy. You can't get those bullets back. Those bullets are now held by these objects that are being moved by those bullets. So you gave away the bullets. The bullets didn't come back. You couldn't get them back. So they've left the building with the person. You've changed their direction. So you can understand that's why the energy is transferred. So you never destroy it. You just transfer it between objects, and all of the collision experiments are just to different environments in which you're going to do this transfer, and there's just some simple rules that dictate the transfer. So obviously in the lever example, put the fulcrum in the right place. No, close enough. It's just so obvious to see, okay, this comes down, it hits this surface, the electrons are doing their fighting, this surface absorbs the energy, okay, because it's denser, well, because there's more of it. But if I don't have anything on it, right, it can just plow right through it and just swing the lever around, right? So if this is actually denser, then it's just going to swing the lever around. But what changes the game is the fact that this other object, if you have it on the scale already, now it has the reservoir here. It has the reservoir of this much larger mass. So now this is facing not only itself, but itself plus the lever. And so obviously this is the object that's going to decelerate. It's going to transfer its energy to the lever. The lever is going to transfer it to the object, and it's going to go out. And so in the case of the half mass, clearly it's going to go out with twice the velocity, because now when you're moving this lever, part of the lever down, you're moving this part of the lever up. Obviously there's all kinds of stresses and energy transfers happening in the material of the lever. If I make the lever out of some people pass plastic straw and I have a weight on it, the straw might just bend. Obviously you're using a lever that bends very little, hopefully, and so all of the energy is just being again negotiated. It's a word for when you have currency and you want to change it to another currency, you're just redenominating the energy through all of these little processes. And obviously the process here is this motion is going to be twice the motion of this, twice the velocity. For every little bit this goes down, this has to go up 2 units. So obviously if I have the mass here and not here, it's going to weigh the same, because it's just that I have to move this half mass twice as fast. This decelerates at exactly the same rate. So let's just understand the simple argument. This decelerates at exactly the same rate. The lever moves at exactly the same speed. Everything is identical if this leaves at twice the velocity. If this doesn't leave at twice the velocity, then nothing's the same. Then somehow this hits the lever and it's getting a greater opposition force, and there's more something. But how can it be more? It just has to move less atoms. The battle is between this big heavy thing and this little light thing, okay? This is going to win the battle. So it's just kind of silly to say there's some sort of magical place that all the energy leaked out of. There's a bunch of missing force, missing currency. You could just understanding it as currency. This has a certain currency. Everything has a certain currency, and they're going to share their currency, okay? In terms of the added catches, the currency is in different directions. But clearly it's just a product, a sum. You just add up the currencies and figure out who gets what. And that's it. But it's just a transfer. So you can have a very direct transfer. In the example of elastic things, they can hit each other and one of them completely stops and the other one moves and just takes. All you're saying is that the stuff pushing the electrons in this object just gave the force through the fact that the electrons are constantly excreting their force, and it didn't reflect back. Instead, it was absorbed by the other electrons, and they took the force. And now they're going to all move in that direction. Because it's all in the same currency, it's really easy for the idea of motion to travel from these electrons to these electrons, because as soon as they make contact, they're the same mass, so the atoms move with the same ease. So it's just a matter of pumping the force pushing these electrons into this other object. And it all makes sense. Now, if this object is heavier, then you can understand, well, now there's going to be a problem with the negotiation because this can't leave at the same speed. So now they're, at minimum, going to be stuck together a longer period of time because there's got to be a negotiation. There's not enough little bits to push all of these electrons at the same speed. Just a fact, they're not there. So now you know you're probably going to get a reflection. And that's how it really works. Again, the simple truth is that, the more you move these objects, the less you're going to get in a reflection, and the less these objects move. So say this didn't move at all, and these are heavier and heavier. Obviously, I hit the light one, it all moves. I hit something a little heavier, I get a little less, and a little less, and a little less, and I get more and more reflection. So anyway, alright, so that's probably enough of a video. So just throwing it in as context that although I don't need all of this extra theory to present to you and say this is why I'm really confident, is because frankly it works for everything. To make an argument against kinetic energy, I'm just saying it's just more evidence that what they've presented you as a theory of reality, bent space, is not a physical explanation of anything. They don't have any explanation for charge or electricity and magnetism, nothing. They just say there's a magical functions. The electrons magically repel electrons, and the protons are magically attracted to electrons. It's all just magic. And the fact is they never even thought about push versus pull. In all of what I've explained here, there's no such thing as a pull. There's just an absence of a push. So, so it also makes sense, and that's more elemental, right? This is almost like, arguing I don't need to give my horses carrots to get them to do work. I could just have a whip, and every time they do what I want them to do, I don't whip them, and I'll get the same effect as a carrot. I'll get the same effect as a pull, but it's not really a pull, if you get my drift, right? So the elemental universe is really just made out of the one mechanism. There's not a positive and a negative. There's just the positive or just the negative, and all you're saying is when the negative isn't there, it's positive, and when it is there, it's negative. That's simple. So anyway, maybe I'll just pop the. Ooh, yeah, that wasn't too good. It's too much junk. I gotta clean up my life. All right. Yeah, that's funny. I did it to the wrong camera. Got it. I have to do this camera. Yeah, that'll work. So that's where the simulation is. So as you can see, it's just perfectly green, red, green, red, green, red, green, red, green, red, and it can fold and create more complex objects. And again, this just isn't quite done. So, the guy who's been working on it for years has been very distracted lately, so not much has been accomplished to just tie up a couple of loose ends. But it's very close. And you can just see that obviously if an electron and proton close to each other, well, that's something I should probably talk about because it really is irritating physics. They say that a proton is hydrogen. Then they say a proton and electron is hydrogen. But a proton and electron is also a neutron. So really you could understand that when the proton and the electron are far apart and jiggling a lot, that's hydrogen. When they're really close, that's a neutron. All right, and then you can see the process you could make the electron proton-proton combination. And let's just say protons were twice as heavy as electrons, then you can understand why they don't do a bunch of moving and end up in nucleuses in the higher proportion. But you could understand that once you've created that, you don't need the strong force, okay, and that you create all kinds of opportunity for mayhem. So part of the simulation eventually will be where I could just pop one of these things in and out of existence. So I could just all of a sudden remove that red thing between these two green things. And you could understand that, well, now the green things are going to repel each other rather intensely. Because they have a bunch of red force being turned into green force here, and red force being turned into green force here, going to be hitting each other with a lot of force, and there's going to be a great desire for them to separate, and that's going to break everything else. So you can understand that when they're able to send something into a nucleus and hit it with enough energy in a tiny amount of space, because it's a tiny space, the nucleus is a tiny thing, and the energy you're throwing at it, you have to understand a photon is bits of energy, just like this stuff. And you have to get a bunch of bits to hit at the same time in this tiny area. And you can understand that if everything's jiggling around, how can I send little bits that are following each other in sequence? Really going to be really hard to do. So if I'm scattering my machine gun, I can't really hit one spot with 5 bullets. So that's why it's so hard to hit a nucleus with the energy needed to expel or actually eject an electron. You have to hit it with enough energy where it feels enough pressure to actually leave. And so it's really hard to hit one. And it's not just because nucleuses are small. The better answer is it's because our guns suck. I mean, we can't shoot straight because of the Browning motion. So again, it all kind of ties together. Too much jiggle. All right, anyway. Yeah, that's really... So enough, okay. So you could just go on and on with every subject. You can start talking about rocket ships and ballistic pendulums and all kinds of other mechanisms, and talk about the fact that you have to conserve this stuff. So this stuff, like this, you could call it heat. The universe is hot. This is its temperature, the amount of these little bits flying around free. And what absorbs the temperature is matter that captures some of those bits in one direction and creates a deficit in that direction. So instead of the force bit going the speed of light, it's going something much slower, pushing the matter. That's the deficit that creates things like gravity. And so you're really just thinking about this as heat, and you can sort of understand that I can turn heat into something powerful when I can get it to go in one direction. So the matter sort of enables you to create beams of this randomish stuff, and those beams are capable of, causing a bunch of electrons and protons to scatter in all kinds of directions and break the structure that you're hitting with the beam of force. So heat is momentum, and momentum in matter is just giving heat a direction. So instead of going in all directions, it's going in one direction. All right, so that might be enough. So till the next time, and such and so forth and whatnot. I can only do my part here. The fact is, you people are just really uninterested in science theories. You're uninterested in having a reasonable conversation about the mechanical truth, and all you really want to do is defend religions. And that's your prerogative, but I'm going to call it what it is, which is despicable. You're wasting. You have no. You might as well not have something called intelligence, because you don't know how to use it. You don't know the rules of being intelligent, which is you have to be open to reasonable conversation. And everything I've said in this video is a reasonable conversation. Part of reasonable conversation. You have no reason to be confident in your bent space, mushy, non-physical force perception of the universe. A real physical force theory can explain. You just won't let it explain.